Here is the continuation of theorem 29.1. Okay, so let me continue from this. You are proving Y is a topological space. Okay, so to prove this you have to prove three things. Okay, so let me show you that. This is the first part you are proving to say Y is a topological space, and then you will prove finite intersection of open set in Y is open in Y. You have to prove this, and then you will prove arbitrary union of open set in Y is also open in Y. Okay, these things you have to prove to say Y is a topological space. Is that clear? Okay, let's start with this. The empty set. Take empty set. Okay, first what you have to prove this, what you have to do, you take a empty set. Empty set is denoted by pi. You all know that, right? Okay, pi. Okay, listen, the empty set is open in where? X, and it will be open in Y. Empty set is always open in X, topological space X, and topological space Y. It is open in both the spaces. So that is what you are writing. Also, you are taking pi is compact subset of X. You are taking like that. You are taking like that, compact subset of X or subspace of X. Both are right. So, okay, you are writing like that. Now, what you are finding is Y minus pi. What is Y minus pi? You know that. Pi means empty. When you subtract empty from Y means you are going to get Y. Right? So that is what you are writing. Y minus 0 is Y? No. So that is what? Y minus pi equal to Y. Is open in Y. How you are writing? Because you know that open set in Y will be in this format. Y minus C. In the place of C, here you are having pi. That's the only difference. So you know that the C, okay, the element present here will be the compact subspace of X. Here also you are taking the element present here is the compact subset of or subspace of X. So it is in that format, you know. So the sets present in where will be in this format? The open set in Y will be in this format. That is how you are defined. Am I right? Right? Okay. So using that you are saying Y minus pi equal to Y, and this will be what? Open in Y, because it is in that format as we have defined like that. You defined like that, right? So you are writing like that. Is that clear? Now let's prove finite intersection of open set in Y is open in Y. Shall we? Okay, to prove this, here you are having three cases. Case 1, case 2, case 3. Case 1. In case 1, you are taking two sets. What are they? U1 and U2. In here, you have defined U, the sets U are open in X. Okay. So, from here only, you are taking U1 and U2. So, U is open in X means U1 and U2 will be also open in X. No. So, that is what you are writing. Let U1 and U2 are open in X. So, even when you find the intersection of these two U1 and U2, that will be also open in X. Am I right? So, that is what you are writing. Is there any difficulties? No, right? So, let's pass on to case 2. In case 2, you are taking this sets, this kind of sets. Y minus C1, Y minus C2. You are taking two sets. Okay. You know that these two are open in Y. Because you define like that. The open sets in Y will be like this. All sets of the form like this. Open sets in Y will be in this form, right? So you are taking that kind of sets. So you know that these two are open in Y, and you know that open in Y means this C1 and C2 will be what? Compact subspace of X. That is what you have defined. From that you are writing. So you are finding the intersection, because you are finding finite intersection of open set in Y is open in Y, right? So you are finding intersection here. So intersection that will also is going to be open in Y, because if these two are open in Y means the intersection of that two open sets will be also open in Y. So that is what you are writing. Can you understand me? Okay. Now let's pass on to case 3. Let U1 is open in X. Here you are taking one set from here and another one set from here. Okay. So in case 1 you took two sets from here. In case 2, you take two sets from here. But in case 3, you will take one set from here and one set from here. another one set from here. Is that clear? Okay, let's see. That u1 is open in x. You know that from that from here u means open in x. So u1 is also open in x. You know that y minus c1 will be open in y. Is there any confusions? And you know that this c1 will be open subset of x. Is that clear? Okay. Now you are writing about this c1 here. Okay. C1 is the compact subspace of x, right? X is a Hausdorff space. X is a Hausdorff space. X is a Hausdorff space. Sorry, here also you have assumed it. Sorry. Here you assumed it in the step 2 in the beginning. You assumed that X is a locally compact Hausdorff space, right? You are using that here. In this place only you are using that. Before any other steps you didn't use that, right? Okay. So here you are talking about C1 is the compact subspace of Hausdorff space X. Compact subspace of a Hausdorff space is closed, right? So here C1 is closed in X. Is that clear? So if C1 is closed in X means this X minus this C1 will be open in this X. Okay, so that is what you are writing. X minus C1 means, look at this. Here you are having X, no. So here you open in X. Sometimes you may get confused. If you are having no proper understanding, you may think, because I thought like that when I am learning this. Okay, so X minus at the time of writing examinations, I will get confused. Oh my god, is there Y or X? So bad. Okay, so X minus C1 means X minus C1 open. Here you should not have any confusions. In X, this X, okay, look at this. Here X, no, so here also X. Okay. Now we are finding the intersection of this and this. That will be open in X because this is open in X. So intersection, you are finding intersection that will also open in X. Look at this, look at this, look at this. This is open in X, this is also open in X. So when you find the intersection, that will also open in X. Similarly, when you find the intersection of u1 and y minus c1, okay, if you do like this and if you find the intersection of u1 intersection y minus c1, that will open in y. Okay, this is open in X and this will be open in Y. So that is how case 3 is coming to an end. So this line I am having little bit of confusion, no proper understanding. Okay, anyways, can you understand this? Now let's prove arbitrary union of open set in Y is also open in Y. Now you are proving the union part. Proving union. Okay. So let's see, you are taking collection. Arbitrary union. No, you have to take collections. Okay. Collection. Let U alpha be the arbitrary collection of open set in X. U is open in X. Already you are having. Again and again I explained you. U will be open in X. That is how you defined, right? So here also the collection U alpha is also open in X. So when you find the union, here you are proving union. No. So you are when you find the union of this collection, that will also open in X. That is what you are writing. Now you are taking Y minus C beta. Because this is you are talking about collection, no? So that is why beta, in general you are saying beta. C1 suffix can change 1, 2, it takes so many values. So that is why beta in general you are saying. Y minus C beta is the collection of, tell me, open set in Y, right? Because all open set in Y will be in this format. That is how you defined. Okay, collection of open set in Y. Here C beta is a compact subspace of X. Okay. Okay. Now you are finding the union of this. From this to this step you will get by De Morgan's identity. You can write like this: Y minus, when union comes to this term becomes intersection. So Y minus you are putting, instead of this you are putting C, where C equal to this you are writing. You know that C, this is the compact subspace of X. This is in this format, right? If in this format means what? This is open in Y, right? If this is open in Y, left hand side will also open in Y. So that is what you are writing. Okay, now let's 3. 3 means you are taking U alpha collection and another 2 sets you will take. U alpha collection and Y minus C beta collection. So you are taking like that. You know that this is open set in X and this is open set in Y. Here C beta is a compact subspace of X. Everything you know. Now finding the union of this and this. Okay. So here what you are doing, y minus, you are bringing this union to this side, so it becomes intersection. So here instead of this you can put u union y minus c. How? This value is c, no? Just above you wrote it, this value equal to c. So you are writing y minus c. So from this to this step you can write like this, y minus c minus u. You can write like this. So this becomes that format, y minus c form you brought it. So you can say this is compact subspace of x. Y minus c format means that c is the compact subspace of x. No. So that is here c minus u, having in the place of c, here you are having c minus u. Therefore you can say this c minus u is the compact subspace of x. So this is open in y means the left hand side is also open in y. So you proved all the conditions to say y is a topological space. Finally you proved y is a topological space. Am I right? Now let us prove x is a subspace of y. What is that? X, the topological space x is a subspace of the topological space y. That is what you are going to prove. To prove that, what you have to prove, the intersection of any open set in y with x is open in x. If you prove this line, then this will be automatically proved. The intersection of any open set in y, that is, you have to take an open set in y, that is y minus c. You know that open set in y will be how it looks like, right? Y minus c is the open set in y. So you are taking y minus c and your intersection of any open set with x. So open set intersection this x is, this is open in x. That is what you have to prove. Can you understand? I'm sure you can understand. If y minus c is open in y means, then you are writing y minus c intersection x. The value of this is x minus c. Okay. Y minus intersection x, c is what? Intersection x is what? X minus c. Okay. So here this is open in x. Okay. X minus c is open in x. Y minus c means you will say open in y. X minus c means it will be open in x. That is what you are writing. So if this is open in x and c is the compact subspace of the Hausdorff space x. Okay, x is the Hausdorff space. So first you are writing about this, x minus c is open in x, and you are talking about the c now. C is the compact subspace of x. X is a Hausdorff space. Okay, that's what you are writing in the sentence. So if this is open in x means the left hand side will also open in x. So you proved it finally. You took intersection of any open set in y with x, and finally you brought it that is open in x. Therefore you proved it. No. So now you can say this x is a subspace of y. Is that clear? Okay, let me pass on to the next. Now you are going to prove the constructed y space. You are having that y space. No, that y space is compact. That is what you are going to prove. So to prove this y something is compact, you have to take an open covering from that set. Okay. So here you have to say y is compact. So from y you are taking an open covering, that is script A. Let script A be an open covering of y. Now the collection script A must, it's an open covering of y. It means what? Open set of y. Open set of y means it will be in this format, right? So that is what the collection script A must contain an open set y minus c. Because it's an open covering of y. Open covering or open set, everything is related to each other. So it's an open covering of y means the open set in y will be in y minus c format. Therefore, the collection script A must contain an open set like this. That is how we are writing. Therefore, the corresponding finite subcollection of elements of script A along with the element y minus c. So here you will have open covering some elements. That elements with this element. These all covers what? These all together cover this y. Therefore, you can say y is compact. Okay. You proved it. The open covering is covering our y. That is how you proved it, right? So now you proved by the definition of compact, you proved y is compact. Is that clear? Now let's prove this y is Hausdorff space. To prove y is a Hausdorff space, you are taking 2 points from y. That by the definition. What is that? Hausdorff space definition is what? Tell me. That is important. because we have learned it earlier. No, tell me, what is if you want to say y is a Hausdorff space means what? You have to take two distinct points from that y, and for that distinct points, different points, what you have to take? You have to take a neighborhoods of that distinct points. That neighborhoods of that points should not be the neighborhoods of that points should be distinct. Neighborhoods should be distinct. They should not have any common values. Okay, they should be disjoint, distinct. Neighborhoods also distinct. Distinct points have disjoint neighborhoods. That is what the definition of Hausdorff space. So to prove that, first you have to take 2 points. No, you took that. So okay, now with the help of x, already you are having x is a Hausdorff space, x is a Hausdorff space, already you have wrote it. So with the help of x, we are going to prove y is a Hausdorff space. Is that clear? Okay, let us prove that. You are taking, already you are having x is a Hausdorff space. You know that it means it is satisfying the condition of Hausdorff space. There will be 2 points in x and the neighborhood of that 2 points is disjoint, right? Already it is there because already x is a Hausdorff space. No, so it is satisfying these conditions. So you are writing that since suppose x and y are points of x is a Hausdorff space means there exists disjoint open sets or neighborhoods. Neighborhood is always open. Okay, neighborhood and open set are same. Okay, disjoint open set u and v, that is for x the neighborhood is u, for y the neighborhood is v. That's what we are writing. Now suppose x belongs to x, this point x belongs to capital X, and y equal to infinitive means, and x is locally compact means x is locally compact. So by the definition of locally compact, there will be a compact space. Within that compact space you will have a neighborhood. Okay, that is what the definition. So here using, you are taking like this, x belongs to x, y equal to infinitive, and this x is locally compact. Therefore we are choosing a compact space because by the definition of locally compact you have to take it. You have to take a compact space. So you choose a compact space. The name of the compact space is C of x. From x you are taking, no, so of x. Containing this compact space should have a neighborhood of what? For this point you are taking a neighborhood, no? That neighborhood, what's the neighborhood? For x, what is the neighborhood? U. That neighborhood present inside the compact space. How you are writing all these stories? Because x is locally compact. Okay. Since C is the compact subspace of a Hausdorff space x. From this line you are writing C is a compact subspace of x. X is a Hausdorff space. So you are writing. Therefore you can say compact subspace of a Hausdorff space is closed. So C is closed in x. If C is closed in x means x minus C will be open in x. Oh God, what's the sentence they are writing? C is, sorry, I did not see that. Okay, I am in the flow. Okay, C is closed in x. Therefore y minus C is open in y. Oh. X is converted into y here. Why? Oh God, doubt arised. Okay, so after this step what you are writing? This y minus c contains infinitive. Therefore you are having here u and y minus c. These two are disjoint. Therefore you can say there exist disjoint neighborhoods u and y minus c of, for the point x you are having neighborhood u, and for the point infinity you are having y minus c. So you got distinct points. For distinct points you got disjoint neighborhoods. You can say y is a Hausdorff space. Sometimes maybe x is a subspace of y. That is why you converted x story from y story. Is that clear? X is a subspace. Oh God, that's the point, man. X is a subspace of y, no? So that is why here x converted into y in the next step. Is that clear? You can write that. Okay, so let us prove. You proved y is a Hausdorff space. Now let's prove step 3. As you are assuming these 3 conditions. Okay, and you will prove x is locally compact Hausdorff space. Shall we? Already you proved. What proved? Y is a Hausdorff space is already proved. So let us prove it's a locally compact Hausdorff space. Let us prove locally compact. That is what you have to prove now. Okay, by assuming these three conditions. Okay, let's start. X is a subspace of Y. You proved it. And Y is a Hausdorff space. You proved it also. So if X is a subspace of Y, this Y is a Hausdorff space means what you can say? You are having a theorem. Subspace of a X is subspace of Hausdorff space. Therefore, you are having a theorem. Subspace of a Hausdorff space is Hausdorff. Therefore, you can say now X is a Hausdorff space. Is that clear? So you proved X is a Hausdorff space is proved. Now let us concentrate to prove X is locally compact. Okay, let's proceed. To prove the locally compact means you know that. You have to bring that story to say a set as a locally compact means what? There should be a compact space. Within that compact space, you have the neighborhood. Right? That is what the definition. So, let's see what to do. To prove X is locally compact, you are taking a point from X, small x, and you are going to say this X is locally compact at this point X. It means for this point, there is a neighborhood and that neighborhood is present inside the compact set. Then you can say X is locally compact. That story is going to happen. Let's see how. You are taking two distinct points of Y, X and infinitive. Already you are having from Y, you are taking two. These are the 2 points you took from Y, right? And you said for these 2 points you are having disjoint neighborhoods. That story you have wrote. So from that you are taking X and infinity are the distinct point of Y. Since Y is Hausdorff, you know that there will be disjoint neighborhoods U and V. U is the neighborhood of X, V is the neighborhood of infinitive. Yeah, this story you know. Since V is open in Y, okay, V is open in Y means Y minus V will be closed in Y. You know that story. Since Y is a compact space, right? If V is open in Y means when you subtract this V from Y, when you subtract this open set from Y, the resultant will be what? Closed in Y. That's what. Since Y is, you are talking about this Y. Y is a Hausdorff space. C is compact. C is compact. Okay. C lies in X. You are saying this compact space lies within X. So Y minus V is a compact subspace of X. Compact subspace of X. C is subspace because it lies in X, right? C is compact. Therefore, you can say C is a compact subspace of X. The value of C is Y minus V. You are taking, right? Easy. Nothing is here to feel confused. C lies in X. It means C is a subspace of X. Is that clear? So, C is a subspace of X. Now, compact. In the above line, you said C is compact. So, you are attaching all these things and writing in one sentence.